Before we begin calculations using the method of initial rates, let's write the rate law for the reaction of NO and H2. Rate is equal to K, the rate constant, times the concentration of NO to the M power times the concentration of H2 to the N power. To determine the exponents M and N, we need to use the method of initial rates. In this method, we're going to choose two experiments to work with where one concentration is varied and the other remains constant. So I'm going to choose experiment 1 and experiment 2 because the concentration of NO changes, but the concentration of H2 remains constant. I'm going to plug in the values from each experiment into my rate law expression. So for experiment 1, the rate is 2.835 times 10 to the minus 3, and that will equal some value of K times the concentration of NO, which is 0.30, and that's raised to the M power, times the concentration of 0.35, raised to the N power. I'm going to do the same thing for experiment 2. Experiment 2 has a rate of 1.134 times 10 to the minus 2, and that will equal some rate constant K times the concentration of NO, which is 0.60 raised to the M power, times the concentration of 0.35 raised to the N power. Now we can set up a ratio of the two rates and the two rate laws, which will give us an equation, and we can solve for each exponent. So before we solve, let's cancel things out. K will cancel out, and so will 0.35 raised to the N power in the numerator and the denominator. And that leaves us with 2.835 times 10 to the minus 3 divided by 1.134 times 10 to the minus 2 equals 0.30 divided by 0.60, all raised to the M power. If we simplify, we end up with 0.25 equals 0.5 raised to the M power. We could use logarithms to solve for M, but sometimes if we turn the decimals into fractions, we can figure out what the exponent is without doing any calculations. So 1/4 is the same as 0.25, and 1/2 is 0.50. We can see that 1/2 times 1/2 will give us 1/4, and so in that case M is going to be 2. So we've solved for M in our rate law, and now we can do a similar calculation to solve for N. To solve for N, let's choose two experiments where the concentration of NO remains constant, but the concentration of H2 changes. And that's going to be experiment 2 and 3. And just to show you that it doesn't matter which order we use the experiments, this time I will compare experiment 3 to experiment 2. Just as we did above, let's set up a ratio of the two rates and the two rate laws for experiment 3 and experiment 2. So the rate in experiment 3 is 2.268 times 10 to the minus 2, and that's going to equal the rate constant times the concentration of 0.60 raised to the M power times the concentration of H2, 0.70 raised to the N power. And experiment 2 has a rate of 1.134 times 10 to the minus 2. That's going to equal the rate constant times 0.60 raised to the M power and 0.35 raised to the N power. Let's set up our equation, and cancel out terms that we can. The k's cancel, and this time 0.6 raised to the m power divided by 0.6 to the m power can be canceled out. That's 1. And we end up with 2.268 times 10 to the minus 2 divided by 1.134 times 10 to the minus 2 equal to 0.70 divided by 0.35 raised to the n power. Simplifying, we get 2 equals 2 to the n power, and hopefully we all can see that n is going to equal 1. We've solved for both exponents in our rate law, so let's rewrite the rate law for this reaction. Rate equals K times the concentration of NO squared times the concentration of H2. Now that we have the rate law, we can determine the rate constant by plugging in any experiment data into the rate law. So let's just pick an experiment. I'll choose experiment 1. The rate of experiment 1 is 2.835 times 10 to the minus 3 equals the rate constant times the concentration of NO, which is 0.30, and that will be squared, times the concentration of 0.35. Solving for K gives us 0.090. And we need to determine the units of the rate constant, so let's look at our rate law. The exponents add up to 3. Remember, there's a 1 here that's generally not written. And so we have a third order rate law, which tells us that the units should be molarity to the minus 2, seconds to the minus 1.